Today, we are going to talk about a rule that is so fundamental it runs everything, from a star exploding in deep space to you just picking up your phone. It's the law of conservation of energy.
Okay, let's just dive right in. Take a look at this pole vaulter. As they're sprinting down the track, they're building up kinetic energy. You know, the energy of motion. Then they plant the pole. It bends like crazy, storing all of that forward energy as elastic potential energy. And then whoosh, as the pole snaps back, it launches them sky high, turning all that stored energy into gravitational potential energy. It is a beautiful, perfect example of energy just changing from one type to another.
But what about the end? When they come down and land on that big mat, where does all that energy actually go? Does it just poof, disappear into thin air? That's the big question we're going to get to the bottom of today.
Now, to answer that, we've got to lay down a few ground rules first. Let's quickly cover the core principles that energy has to follow, no matter what.
It all kicks off with this really important concept in physics, conserved. It's a fancy word, but all it really means is that the total amount of energy in a system never ever changes. It stays the same.
So this means it can't be created, you can't just snap your fingers and make energy out of nothing.
And on the flip side, it can't be destroyed either. It never just vanishes. It always turns into something else. So if energy isn't being made or destroyed, what is happening? Well, think of energy as being kept in different stores, kind of like you have money in different bank accounts. You've got chemical energy in the food you eat, kinetic energy in a car that's moving, thermal energy in a hot coffee, and a whole bunch more.
All right, so if energy lives in all these different accounts, how does it move between them? Well, this is where things get really interesting. Let's talk about the great energy transfer.
And this is happening all around us, all the time. The chemical energy locked inside an apple gets transferred into the kinetic energy of a cyclist pushing the pedals. The chemical energy in a battery gets transformed into the light and heat that come from a flashlight. It's just this constant, endless flow.
So the real key takeaway here is that every single thing that happens, a flower growing, a car driving, you just looking at this screen, it's all just energy moving from one of those bank accounts to another. The grand total never changes, it's just moving around.
And all of this leads us to one simple, incredibly powerful rule that governs every single one of these transfers. I like to call it energy's golden rule. What you put in, you must get out.
And here it is, the official law of conservation of energy. Energy cannot be created or destroyed, only transferred or changed from one form to another. This single sentence, it's one of the absolute cornerstones of all of science. Period.
So how can we actually track all this? While scientists use these cool things called energy flow diagrams to map out exactly where every last bit of energy goes, it's like a visual receipt to prove everything is accounted for.
Let's use this lamp as an example. We start by putting in 100 joules. That's just the unit we use to measure energy. So we've got 100 joules of electrical energy going in. That's our input. Now, that electricity gets converted into two main outputs: light, which is what we want, and heat, which is why the light bulb gets hot. And if we measure it, we find only 10 joules becomes useful light, while a whopping 90 joules is given off as heat. But here's the magic. Add them up. 10 plus 90 equals 100. The output perfectly matches the input. None of the energy was lost.
And this rule holds true for everything. Doesn't matter how complicated. Check out this car engine. 100% of the chemical energy from the fuel goes in. Now look what comes out. Only about 25% becomes kinetic energy that actually moves the car. 35% is lost as heat and sound, and another 40% is still in the exhaust. But add it all up, and what do you get? Exactly 100%. It's a perfect balance.
All right, now it is your turn to be the detective. Let's see if you can take this golden rule and solve a couple of cases.
Okay, first case. Look at this diagram for an electric motor. We're putting in 1,000 joules of electrical energy. We're getting out 500 joules of useful kinetic energy, to make it spin. So based on the rule, how much thermal energy, that's our X, has to be produced? I'll give you a second to think it over.
Did you get it? The input must equal the output. So 1,000 joules went in, minus the 500 joules that came out as motion, leaves exactly 500 joules of thermal energy. Awesome.
Okay, let's try one more. This one's a little bit of a word problem. Sophia has a flashlight that uses 18 joules of energy from the battery. We know that 7 joules of that is wasted as heat. Now, Sophia claims that 12 joules becomes light. Is she correct? Check the math. And the verdict is, Sophia is incorrect. Remember the rule. input must equal output. If you add up her outputs, 7 joules of heat plus 12 joules of light, you get 19 joules. But the input was only 18. The books have to balance. The real answer is 18 minus the 7 joules for heat, which leaves only 11 joules for light.
So the next time you hear someone talk about wasted energy, remember what you learned here. The energy isn't really gone, it's just been converted into a form that's maybe not as useful to us, usually heat. The universe is a perfect accountant. So I'll leave you with this final thought. Now that you know the rule, look around you. Where can you spot energy changing form? Right this very second.